Today I want to start with Unit 3. So these are the notes. There are a few pages in the book that talk about this, the tools that we're going to use to design programs. In Unit 2, I assigned you a couple of programs, and most of you said, "Oh, this is fun, let's go." And started throwing things onto a form, writing some code, creating a few extra event handlers, deleting those, trashing your program, starting over again, all the good stuff that you do when you write programs. Those are relatively simple programs. As programs get more and more complex, you can't just sit down and start cranking out code. It doesn't work. To learn how to design programs so that when you do sit down, you have a clear path and you're not wasting a lot of time doing stuff that maybe isn't even part of the requirement. Maybe doesn't look the way the user wants and they want you to start all over again. That clear path makes programming a lot faster. Another reason we're doing it because you're required to. It's my course requirement. It's not my course requirement. It is a statewide requirement that you learn how to not only program, but design programs and use the tools, learn to use some of the tools that are available for designing programs. So it's a statewide program requirement. As we've said before, programming is part art, part engineering. I can teach you the engineering part. The art's a little tougher. The design that we're talking about here is not, do you use pink text on purple backgrounds and those kind of things? Does your text show through or is it hidden by the background? Not that kind of design. It's not an aesthetic design, it's more like an engineering design. If we decide to put a new bridge over the Wisconsin River, we don't just throw a bunch of steel over on the bank and start hammering it together. If we decide we're going to build a house, we don't just buy a bunch of wood, a couple of strands of wire, start cranking it out. There's a bunch of design that's involved. Mike's laughing at me like, who would do that? But it's funny how many people sit down and start writing code without designing. And I've mentioned in previous classes that you're going to be spending a fair amount of time with this, both as networkers. You don't just sit down with a bunch of computers and a bunch of wire and a few routers and just kind of plug them in and hope things work as a networker. To give you a better understanding of this, you'll be taking some design classes, systems analysis, first of all, analyzing designs, or analyzing requirements to make sure you understand them. And then systems design for you software developers. How do I take those requirements and document them in a way that programmers, lowly programmers, can look at it and say, okay, I see what you want, crank it out. As software developers, you don't always get to be the program designer. Somebody else may do that. It's an advanced skill. You've got to talk to people who are not technical and figure out what they want. And then translate that into something the technical people can understand. So systems designers, systems analysts are not always the same as programmers, but in a lot of places they are. So you're going to learn all the skills here and hopefully be able to put them together. There's a rule in programming, it's the 40-20-40 rule, that says you should spend about 40% of your time on a new project designing that project, laying it out, doing all the things I'm going to show you how to do here and more. This isn't all there is to design. This is a good starting point. Then about 20% of the time cranking out the code. And then another 40% testing that code. How do you know it works? Most projects are complex enough, most programs are complex enough that you've got to try lots of different combinations of things and make sure everything works. Now, of course, that means our programs, if everything works, have to be idiot-proof, and we're still a ways away from learning how to make programs idiot-proof. But there are some basic features of your program that should work, and you have to understand how to test those. If you find that you're doing my homework assignments and you're spending hours, and Volker said it was only supposed to take 10, and you're on hour 20, you probably didn't design. You said, I got it. It's in my head. I can do this. Crank it out, and I'll do the design after the fact. It's kind of like building a house, showing it to the user, and then calling in an architect and saying, real quick, draw that up for me. And then the user looks in the house and says, that's not what I wanted. It is too. Looks right here on the architect diagram that you built after the fact. Very common mistake. wastes a lot of money. In this class, it's your time. But in the real world, if you're a software developer or a networker and you're working on stuff and you're going down the wrong road, that's money. And that's where these designs come in handy. Very step-by-step process. I'm going to show you a process that is a combination of mine and other tools that I've seen in various books over the years. And I've collected those tools and those steps that I think will help you design programs that you'll be able to crank out relatively quickly. That's my goal. We're going to break those programs down into smaller parts. Object-oriented programming actually makes that a little easier. You've seen event handlers. Many of you are working on your states program and you've got 5, 6 event handlers in there. Each one of those is its own little program. And we can design it. Even though it's simple, we can design it. And even better, we can test it. Each separate object, each separate event, we can test it. The first programs we're going to design are simple. When you learn how to do architecture, you don't learn how to draw Bill Gates' mansion, you learn how to draw a treehouse in the backyard. We're going to be working on tree houses here. Some of these are going to be extremely simple. Well, that's where we start, and they get more complicated from there, I promise. You'll be doing design for the rest of your career in this class, at least. Next semester, the design requirements for software developers, so those of you programming logic intermediate, will be reduced. Okay? Because we don't have to do all of this stuff. But when things get complicated, that's when you fall back on some of these other tools. If we need to fix programs, we've got it broken down into parts, that's easier. And that design that you're going to do, that you're going to spend 40% of your life, of your program career doing, that design actually becomes part of the project. And if somebody else is taking it over, that's usually the first place they look. It is very hard for a maintenance programmer to grab somebody else's program and look at it from top to bottom and say, I got it. As you've already seen, programs aren't written top to bottom. If you alphabetize your event handlers, you didn't write them in that order. That's just the order we list them. And so there's lots of other tools to help people get their head around what this problem is about and how it was solved, and then they can go look at the code where they feel they need to. We're going to develop algorithms. Algorithms are a set of steps. It's not necessarily a program thing. A recipe is an algorithm. Here's the steps that you follow to make a pie. So algorithm is a pretty generic term, but we're going to develop some algorithms which are well-defined steps for solving a problem. They're usually written in English or something that looks like English so that anybody can understand them. Once we have an algorithm, then your job as programmers is to translate that. It's written in English, or it's written in pseudocode, which is close, or it's a mathematical formula that some guy in CSI wrote on the board. And now they want a program to use that formula. Your job is to translate it into something a computer can understand using the language of your choice, which in our case is C#. Then the compilers turn all that into ones and zeros so that we can actually run the program. The technique that I'm going to show you uses 5 levels of design that get progressively more detailed. The first one, what's the application supposed to do, is a very high level picture of not a picture, but a description of what the program's supposed to do. Very high level. You'll see what I mean in a minute. Then step 2 is design the user interface. We're going to call this a prototype. We're going to go into Visual Studio. We're going to launch it. We're going to build a form and say, hey, given what we built in level 1, this is what I think the form is going to look like. We don't write any code. We don't make the buttons work. If you don't want to, you don't even have to name the objects. You don't have to add icons. You don't have to do any of that stuff. What a prototype or a user interface does is it allows you to quickly show to your customer, your user, that this is what I think you asked for. Before you even write any code, it's just a picture, really, of what I think you asked for. Does that look right to you? And sometimes they'll say, well, it's ugly, it's gray, it doesn't have any pictures, doesn't have a form icon. Did you go to Volker's class? What the heck? Right. And you'll go, no, no, just the general, the stuff in there, is that what you're looking for? You can go crazy in the prototypes and throw pictures and icons and background colors and all that stuff in there if that's what you want to, but we're at level 2 design, very, very high level. Make it pretty can happen later. Then we're going to go to a third level and we're going to figure out what are the tasks that the program has to do, T. What are the objects it uses to do that? Objects like controls, O. And then E, what are the events that we expect to respond to? You saw during the Unit 2 lecture that an object can respond to dozens of events. Double clicks and clicks and drags and right clicks and hovers and all kinds of stuff. Your application isn't going to respond to every one of those. Which ones is it going to respond to? And then what is it going to do in that event? But again, we're not using C# code here. We're just making a list. Here's the steps. When the user clicks on this button, close the form. We'll do that for every event that we expect the application to respond to. Then we'll do flowcharting and pseudocode. Those two are actually redundant. However, flowcharting is a very, very valuable skill for software developers and networkers to have. We're going to use the program called Visio. It's different than Visual Studio. It's Visio. If you haven't installed that on your computers at home, you should do so. You can get it from DreamSpark. It's free, but you will need individual keys for that one, so make sure you copy the key. It's always in your account, but it's good to have that when you install it. So you should have that handy because we'll get to that probably next week sometime. We're also going to use pseudocode because that's what most programmers, particularly seasoned programmers, experienced programmers, use to design pseudocode. They'll often scratch it out on a bar napkin because they're in the bar and they go, oh, just got a brilliant, I scratched that out real quick, frame it, lacquer it, and make sure you hang on to it for later. More likely take the bar napkin to work the next day and throw it into Visio or Word or something to make it a little more formal. And then finally we're going to develop a test plan. We're going to plan ahead of time how you're going to test your program. That way you'll know how it works because you'll expect certain results. And if you don't get those results, something went wrong. Most of you figured out I spent some time in the Air Force, and part of my job as a systems engineer was to help develop test plans. Before we put that airplane on the ground, before we put that missile in a silo, we knew how we were going to test it. And we ran it through the tests. And the Air Force signed off, said, if it passes all these tests, we write you a check. Same kind of thing. You can do the same thing here, make test plans. There are software developers who have been promoted to do nothing but develop test plans and then execute those tests. There are software developers. How do we test computer programs? Run them. But if you have to go through 10,000 different tests, how do you test a computer program? With another computer program. Well, how do we know the test program is working properly? How do we test the test program? There's an end there somewhere. But very often you will write computer programs that will stuff things into another program and say, try this. Did you get this answer? Yes. Okay, now try this. And how long does that take? 5 minutes. How long would it take you to do 10,000 steps? Forever. Maybe. Feel like it. But then there's programs involved, and there's all kinds of techniques. We're going to do a simple one. And you're going to plan in advance what you expect your program to do. You're going to come up with some sample test data. Say, when I put this in, I should get these answers. When I put this in, this should happen. Including, if it asks for your age and you type in Volker, the program should go, nope, not taking it. Not 100% idiot proof, but we're going to make them pseudo idiot proof. All the designs that you do in this chapter, Unit 3, you're going to implement and actually code in Unit 4. And if everything works well, you should see and experience how relatively easy it is to code when you have a design all ready to go. And then in Unit 5, you just blow me off and not do it that way anymore. You'll write the code and go, oh, dang, he wants design documents, and you'll reverse engineer it. and build the design documents. Don't do that. You save yourself a lot of time, trust me, doing the design first. So those are the 5 steps. We're going to design and implement 3 different programs, all of them relatively simple. The complex one is a bowling application. My buddy, the league secretary, said, can you write me a program that accepts the bowler's name and the date that we did the bowling, their 3 scores, tell me their series and their average. For those of you who aren't bowlers, the series is the total. Sure, I can write that. It won't remember anything. Right? We're not getting into database applications until next semester. Your programs this semester, they're going to do stuff, give you cool answers, and then they're going to forget everything. Saving to a file, saving to a database is pretty much a whole other class, course. So that's later. For right now, we'll just see if we get these things to calculate and come up with the right answers. That's the complicated one, and that's not terribly complicated. Before that, we're going to develop a little program called meters to yards that converts meters to yards. That's it? Yeah, that's it. It can't do yards to meters? Nope. Can't do kilometers to miles? Nope. Just meters to yards. That's all it does. We're also going to develop another one that converts years into days. So if I'm 56 years old, approximately how many days that is. Scary. Think about all the time I've wasted when I find out how many days there are. But another simple program. It's the treehouse. We're going to design the treehouse and actually code it in Unit 4. And then we'll get to stuff that's a little bit bigger. I promise by the time you get to Unit 6, you'll be aching for the treehouse. Because things will get complicated and the designs will be more complicated. And that's what happens. We got to start small. So that's where we're going to start, is small. Okay, I have asked you to download LibreOffice. If you haven't done so, you might want to do that on the side here because I'm going to OneDrive. So you might open up your browser. There's a couple of things I want to pull from OneDrive. Go to OneDrive and then the programming logic folder. Remember, you use mstcvgall@hotmail.com. Password student. And the Unit 3 in-class folder is there, so now when I start doing things, I'm going to throw it up there so that you can get copies of it if you wish. If you missed class or you couldn't keep up. Most of this I ask you to follow along on so you get some experience. And then you're going to do it in the homework assignment. Before we download, there's nothing much in Unit 3 actually. What we really need is the program design template. Mine shows up as a little green Excel icon because I have Office installed here. Yours might be white, doesn't matter. Find the program design template, right click it and download it to your desktop.
What was your OneDrive account again?
mstcvgall, all lowercase, @hotmail.com. This is a spreadsheet template that I have created to help you through my 5 steps of design. Notice there's 5 tabs across the bottom. Convenience, or not convenience, what's the word I'm looking for? Coincidence? No, not exactly. We're going to start by building an IOP. It's a tool that does that very, very first high level of design. Then we're going to do a screen layout, but we're not going to use the spreadsheet to do that. We're going to go back to Visual Studio. Then we're going to build a tow chart. Remember that was tasks, objects, and events. Then we're going to write the pseudocode. Offline in Visio, we'll do flowcharts. And then finally, we'll use this for a test plan. When you're done, you'll have 2 documents that are part of your design. This template with all the stuff in it and a flowchart, Visio document. You'll also have the starter for a project. Don't have to throw that away. It's a nice start. Should have everything on it. Just I'll pretty it up and put some code to it when we're done. So this is where we're starting. What we hope to do with the IOP stands for inputs, outputs, and processing. When I first found this tool, it was called an IPO, inputs, processing, and output. But after using it for a while, I realized that if I'm going to do some very high-level design, the inputs are generally very easy to figure out. The outputs are generally easy to figure out. And once I know what the inputs and outputs are, then the processing isn't so bad. So I've renamed it, just basically flipped the columns and renamed it, so now it's called an IOP. What we're going to do here is at the very high level figure out what inputs does my program need from either a user or in the future from a file or a database or something like that. In our case, all of our programs are going to interact with the user. Then we're going to figure out what's my program supposed to give them back. And then finally, we start listing the steps. How do I go through that process? Usually it's get the inputs, calculate the results somehow, and then process. That's the very simple overview of it. The input column is just a list of things. Here's the things that I need the user to give me. No verbs, no doing, it's just a list. The outputs are just a list. Here's what I'm going to give the user back, a list of things. And finally, the processing is a list of steps. They're verb-based. You have to do things. So that's your overview. The first program we're supposed to write is called meters to yards. The description is it converts meters to yards. What are the inputs? Meters. We have to give these things names because when we write code, the thing we get from the user, we have to store it someplace. We're going to put it in a container. We're going to label it meters or whatever you choose. I try to keep the names pretty simple. And when you type them into your IOP, they are Camelback. So in that first cell, A2, just click in there and type meters. What other input do we need? What else are we going to ask the user for?
Numerical value.
Of what?
Meters.
That's what that is. The numerical value of meters. We're just giving, they're giving us a number like 100, right? And we're going to call that number, that box that we put the number in, meters, so we can remember where we put it. That was a trick question. Nothing. That's it. But if you know that there's nothing left, then you're on the right track, right? There's no other inputs. So we're done with the inputs. What's our program going to spit out? Yards. And again, we give it a name, and yards is good. Keep the name simple. Try not to abbreviate too much because other people may not understand your abbreviations. I'll occasionally break that rule. It's not a rule, it's a guideline. But these should have good names, and yeah, should they be spelled right? Imagine reading a program where yards is spelled wrong. The variable, those are called variables because they can have variable values in them. We can change them. The variables are spelled wrong. It detracts from your reputation as a programmer to do that. Okay, that's it. That's all we're doing. We're getting meters from the users, and we're spitting yards back out at them. Simple program. Now the processing. The processing is usually 3 general steps. Go get all the inputs. Then do all your processing, calculations, and then spit out the results. Well, what if I have a program that's got 10 or 11 inputs, and after the first 3 I could do some calculations, and then after the next, you have no clue, you can't predict in advance that the user is going to enter the data in the way you listed on the form. Most people are anal like me. They'll start at the top and work their way down. But some people are rebels like Nathan here, and he starts in the middle and then goes to the end, puts one at the top and another one at the top and one other one in the middle and around, and he's just starting to mess that program up. So my advice is get all of your inputs. So over here, we're going to add a verb, and I capitalize it just because I'm anal. What am I going to get? The input, which is called meters. Put a space there. I'm sorry, I missed it. Let's see if control scroll works here. Ha ha ha. Cool. Now you can see it. How many more inputs do I have? None. So I leave a blank line again because I'm anal. It doesn't mean anything. It just separates my inputs from my processing from my outputs. Most programmers are very linear. Now I have to do my calculations. Yeah, but the calculations are kind of tricky. We got to think about it. We got to look them up on the web. We got to do all that stuff. But I know what I'm going to spit out, right? I'm going to jump down here and say, what am I going to display for my user? Yards. When I build my IOP, when you build your IOP, I recommend that you don't be quite so linear. You know you're going to get all your inputs, so you list them separately. You don't say get meters and get the other input, the other input. You say get this input, then get that input, get that input. Each one's separate. It's very hard for users to type 3 numbers in the same box, because what do I put in between? Dashes, spaces, commas? So we don't ask them to do that. If we want 3 inputs, we put 3 boxes or 3 somethings on the form so they can give us that input. So each one of these gets should be separate, using exactly the same name as you have over there. Jesus seems awful trivial. Treehouse. And at the end, we're going to display the results. And if there's 3 of those, you list them separately, because again, we display them in different places. Now, in between here, we got to figure out what to do. How do we get from meters to yards? Notice I said what? At this level of design, it's not how. There's some magic formula, right? At this level of design, I don't want you to go digging out that formula. That doesn't happen until level 4 out of 5 in my design. All I want you to put in here is what do you have to do? I need to calculate, and you can abbreviate that calc if you wish, especially if you can't type. The yards. What else do I need to calculate? Nothing. What if there were 6 outputs? There'd probably be 6 calculations. And at this level of the design, if there's intermediate steps, you could put them in there if you know about them. Or you could leave them out. Sometimes to get from meters to yards, it takes more than one step. I'm going to cheat a little bit. I wouldn't normally do this. But I'm going to move this one down. Let's see, I'm in, oh boy. Now I'm doing LibreOffice. Can I drag? No. I know what that guy does, but I can't move that data by dragging. That's annoying. Cut, paste, okay. Cut and paste. I happen to know how to calculate meters into feet. But that's not what the program asks. So I'm going to just add a second step here, just to show you that you can. It isn't always this complicated. Often it's simply calculate every single output, calculate your outputs. That's often all it is, but it could be more. Treehouse. This one's kind of simple. I'm using LibreOffice here. It should be pretty compatible with Excel. So, I was trying to drag because I can do that in Excel. It won't let me do it here. I can go back to Excel later. There's no advantage of LibreOffice except it's free for your virtual machines. Let's save that. Do me and everybody else a favor. When you're saving a LibreOffice document, don't use their open spreadsheet format stuff. It should have a Microsoft Excel 2013 XML document format there, XLSX. Save it as that, and it'll be much easier for everybody else to recognize and open later when they're using Excel, and especially me, because that's what I grade with. And I would put it on your desktop so you can find it. You can always put it in a folder, do whatever you need to. And let's see. And quit asking me. This is my first time using, except for opening it real quick, the Libre spreadsheet. So I'm struggling a little bit, that's why. IOPs, relatively simple. In the inputs column, list what you expect the user to give you. In the outputs, list what you expect the user to get back from your program. And then in the processing, list the steps. And it's usually get the inputs, calculate the outputs, and then display the outputs. This one's just subtly different. Hint, hint, it's about the only one you'll see that's different. I'm just making a point that it can be 5, 6 calculations to get there. Imagine the CSI formula on the board, right? Big old huge thing takes up the whole whiteboard. Now you're supposed to turn that into something. And at the end comes out one number. It might take 17, 20, 30 calculations to get from all those inputs to one output. You can listen. Close that. Okay, mine's saved on my desktop. Didn't I title it? I hope you did. If you didn't, if you followed me, rename it. Let's call this one meters to yards. It's Windows. It can have spaces in it. Later on, when we write the program, the project won't have spaces in it. If you prefer not to put spaces in it, you don't have to. Notice when we use the template. This is a template. Okay, it's an XLTX file, not an SLX or SX, I can't say it, SLSX file. It's a template. That means it's a starting point. When you hit save, it didn't overwrite my template. It asked you to save it in a new location. So now I can use that template to create the next design. Your turn. I'm going to pause the recording. I want you to just give it a shot. It's another easy one. You ready? Convert years to days. I want a program that converts years to days. Give me an eye up, and we'll compare notes here in just a second. Okay, so here's my answer to that. Years and days, those are variable names. Variables are what we use in programming to store values. They're called variables because we can put different variables, different values in them. They vary. Variable names are Camelback, so we're going to get used to using Camelback notation for these things, no spaces. Inputs and outputs, pretty simple here, and then get the years, calculate the days, display the days. We don't read, we don't extract, we just get. It turns out from the screen, our inputs. We calculate days, we abbreviate that to calc, it's okay, and we don't print, we display. All of our programs are going to display their results. If users want to print them, they're going to have to take a screenshot, stick it into Word, and print it. We're not going to give them, there is really no good, easy way to print. And then John's question was, can I put a formula in there for days? Because I know it's times 365.666 or whatever it is. The answer is no. At this level, I want you to tell me what you need to do, not how. How am I going to get the years? There's all kinds of ways I can do that. I'm going to figure that out later. How do I calculate the days? We'll figure that out later. At level 4 in the design is when we're going to need that. For right now, just tell me what. Because these steps are going to translate into the toe chart later on. And those commands that you see there in cell C2 and C4 and C6, those actual commands, we're going to pick them up from here, we're going to copy them into the toe chart. If you have equations in there, it's going to mess us up because in the toe chart it says, what are the tasks that we have to do? It still doesn't say how. It simply says what. All right, save that one. Years to days. Notice I've added the word design to this one. I should have done it to the other. I also discovered file, save as, where are you? Here it is. You can turn this little check mark off, the automatic file extension. If you turn that off, you can type your own XLSX on the end of that. Gotta get it right, XLSX, and it'll save it as an XLS document. Close it when you're done, unless you want to keep it open as an example. And then one more time, double click the template. You're going to use this template, keep it handy. And it's always, I believe it's on my website, it's also on OneDrive. Keep it handy because you're going to use it for every program you write this semester. Double click the template again. In my case, now it's asking me, do you want to use Excel or LibreOffice? I guess I'll stick with LibreOffice, but if you've got the choice, you can switch back and forth. It shouldn't make any difference. And now, once again, because it's a template, I have a brand new, unnamed document ready for me to go. Bowling. My league secretary says, I want to know who did the bowling, I want to know when they bowled, and I need their 3 scores so that you can tell me the series and the average. And the league secretary also wants to put a reminder on there of when they bowl next. Andy's back there going, how am I going to figure that out? Not how. We're not worried about that yet. Wait till you get to that level of design. So, give me some inputs. First thing. Name. Let's make it bowler name. Name is often one. Remember those reserved words that turn blue? Name is often one of those. I don't think it is in C#, but it doesn't hurt to make it a little more elaborate here. What else? Score. Which score? 3 of them. So I have to have 3 different boxes to put those in. I can't put 3 things into one box, variables. So I have to have score 1 and score 2 and score 3. Are those numbers legal? Jesse's going no. I can't start with a number. This was one of those ticket questions, right? I'm in the process of updating that Unit 2 worksheet because it's so lame. I haven't looked at it in years, and I looked at it and said, those are lame questions. Let's put some good ones in there, like what are the rules for variable names or object names? You have to start with a letter or an underscore, and we're never going to start with an underscore. Start with a letter. After that, any combination of letters and digits and underscores. So yes, digits here are perfectly fine. There's one more. I needed to calculate the next bowling date, so where am I going to start from? The date that we bowled. Because league secretaries after bowling, they're usually a little hungover. They don't have time to do all this stuff, so they might do it a couple days later. I'm going to call this the bowling date. Date is almost always a reserved word, so we'll be a little more specific on that one. So in this case, I have 5 different inputs. That's nothing. It's better than 1, but that's not a lot. It's just more. We're getting better. By the way, those last 2 examples, that wasn't even a tree house. That's just kind of like the toolbox that I'm going to carry the tools in when I'm building my tree. So we designed the toolbox. Now we're getting closer to a tree house here. What am I spitting out? The what?
Proper noun. The proper name of a person.
The proper name of the person. Interesting. All right. Let's just make it bowler date. When we display this, am I going to do that? No. I'm not. If the user types his name wrong, we leave it and say, well, that's what, let's say the secretary types it wrong. In the future, it's not a bad idea. I'll teach you how to change whatever the users type so it's all capitalized as beauteously. What else did I need? That was a good idea. I'm going to say no. It's my program. Okay? I'm your user. You're writing this program for me, and you'll say, do you want me to display the bowler name? Well, I just typed it in that box. Where'd it go? Nowhere. It's still there. So no, you don't have to redisplay it. Unless you were printing, which we're not. Then maybe.
Series total.
The total?
Yeah.
Okay. We could call it total. What did you say before that?
Series total.
Series. All right. That's a redundant term. Series total is redundant. Almost capitalize that S. It is good if you know the terminology to use the terminology. Bowlers refer to their total as their series. If you don't know the terminology, guess what? You'll learn it. I know so much about medications, it's scary. Because of the Lions Camp program where they were saying, well, sometimes it's milligrams and sometimes it's this and that. All that, they throw it at me and I go, I've since forgotten it again. But I was pretty good at medications and all the different forms and all the different stuff, and I could even recognize half of them and say, that's not supposed to be a liquid. You get to be pretty good at it. What else do I want? I want the average. Usually you will get these in a printed format, right? Because you get my assignment sheet. Just look at your welcome screen, your stage program. Why didn't we design those first? Because it's boring to start with design. You gotta get in there and do stuff, and you did it. Now we gotta go back and do the boring stuff. In Rapids, I went to a retirement party, not retirement, going away party last night. and my counterpart from Rapids was there. They haven't touched Visual Studio yet. They're doing all this stuff ahead of time, which is a great philosophy, but it's rough in class. In the past, I've seen people go, if this is programming, forget it, I'm not doing this, I'm out of here. It's not. It's part of it. That's why I let you program for a unit, then we do some design, and then we get back into the program. And one last thing, anybody remember what I asked for?
The next bowling day.
The next bowling, good, date. This is hard to visualize, but we're going to take care of that next hour. All right, the visualization of this will come when we do the screen layout. Okay, you got 10 minutes to do two things. Do the processing column best you can, take a break, and come back and we'll talk about it.